My name is Jun. I'm working for KSOE, a short for Korea Shipbuilding and Offshore Engineering. It's a holding company of Hyundai Heavy Industries. Today I'm going to share about the DDV-DT project. It's use case 2, virtual commissioning, in this case for power management system. My brief introduction is on the last page, so if you have any more questions about this project or if you want to discuss to collaborating us, then please contact me. There are 4 things to share today. In background, I'd like to share the roadmap of KSOE in digital field and what we have been doing for that. And the process I went to show to get the DDV-DT AIP. And in modeling and testing chapter, it's about how it goes from the test platform the KSOE has been making to the OSP. In this case, STC. And in results chapter, I'm going to share the result simulation test platform from the OSP in this case, and the modeling process to ensure the reliability of modeling. And in further work, I want to talk about what I needed when I was using OSP. Okay. We have done some project with another ship classifications. Yeah. So we got 3 certificates from them. That is a kind of strategy of KSOE back then. We had our own test platform, so we wanted to extend our test platform as itself. But now we are strengthening the partnership with the DMV. So in 2018, so we got a kind of certificate from DMVGO back then. It was about generator engine model and virtual environment. After deciding to join the OSP JIP in 2018 here, I was a kind of visiting researcher in Trondheim at NTNU. After that time, our company has had a few years to do some projects. So in 2019, we did one of JDP project with the DMV. It's for gas system using a kind of OSP. I don't think it's exact OSP, but it's a kind of OSP here. And after that, we have done a 3-year project with NTNU here. It was just finished this year. And also we started the DDV-DT project last year, and we got a certificate called SOC, Statement of Conformity. It's about model assurance thing. And we have planned to continue this project 2 or 3 more projects until 2025. After many discussions for a few months with Stanley, he is one of the digital specialists in DMV, we decided to do DDV. And chose DT, digital twin, as a qualifier in this case. And one of the target system was PMS, the power management system, which was one of my research interests. And I have modeled several times for a few months. And I did a kind of workshop called RAMOC, Risk Assessment Model Qualification. And I got some feedback and advice from DMV experts. Also, this workshop is to check and confirm the limitation and reliability of model. And the DMV experts I met at workshop through just a video call. They visit to Korea, and we share the experience and some knowledge for digital twin or digital technology. And this, we were testing the PMS is located in local here, connected to a simulation trust center. So we were testing the main functions of PMS. And I got finally DDV-DT AIP in August of this year. And in September of this year, the AIP ceremony and signing MOU were held in Milan, Italy. So there is a link for news. So if you have more interest, then just check this link. It's quite good. So as I said on the previous page, there's some region for doing project with another ship classification because we have each research department in charge of the development of each system, such as power, gas, engine, or ship operation, or even design. So they have their own experience in modeling, and also they have some appropriate equipment to calculate and to simulate. And also they have sometimes proper communication protocol for each purpose. But even though these circumstances, we agreed on the values of the OSP. So we decided to shift our digital model to the OSP. So we started with the power system model as a first project, and we have planned to continue to shift our digital model to the OSP, including the engine and gas and HMI 3D motion and control system. The IAS means integrated automation system. This is a process of how I model the power system usually based on the single line diagram. I modeled all of components of power system using special software to use this real-time simulator called OpenRT and using basically MATLAB Simulink. And I modeled these ship power systems such as generators, circuit breakers, switchboard, including a local controller like governor or AVR or something. And I usually reflect the parameters from datasheet as much as I can, and compiled my model and download them to the real simulator and connect it to power management system. Then we can test the PMS functions using this device. This is the process I went through to get the DDV-DT AIP. At the first time, I made operative version because I want to have a certain reference before I make the FMU files. So this is switchboard, including the input-output interfacing with power management system and including the circuit breakers, several circuit breakers. So I consider that as a port interfacing with other FMU. But in this case, this is operative version. So there are several cores to computate the digital models in parallel. And I separated them as several FMUs file here. This is the switchboard, including circuit breakers and IO ports, and 2 generators and 1 heavy consumers here. So I made operative version. I confirmed them to FMU, and I simulate them together in this Simulink software, and also on the OSP, the local one. So I did this routine many times because sometimes some errors happened. Then I need to check my model and the interface on OSP as well at the same time. And after this workshop 8 times, I got some feedbacks, and I finally changed my model. And after this workshop, these documents were made by our side for SA, supply assurance. It includes test procedure, iris, interfacing with power management system, and use case and conceptual model and model design contract. These 2 documents were used for this RAMOC. User manual and statement of conformity. This came from DMV at the step of MA, the model assurance. It's a kind of certificate. So after that, before DMV visit, I had to finish this model. So I did almost the same routine as MA here, because I needed to make my simulation, my model interfacing with STC this time. So I checked my model in this routine, and finally I simulate my model on STC, Simulation Trust Center, that is interfaced with the PMS. So there are several test procedures looking like this. So I was ready for testing in May of this year. This is operative version I made. PMS is one of these digital models. There are several cores to compute the digital model in parallel, because we need to ensure the real time in this time. So there are 2 main switchboard, including 2 generators and several circuit breakers and boost tie, and there are heavy consumers such as LD compressor, ballast pumps, and something, and including the cargo switchboard and low voltage switchboard. So there are several HD dynamic components, including the local controller, like governor and AVR. So which means we should model just not only dynamics, but also this control module and the module to be controlled by PMS here. This is about power measurement functions. So it includes generator controls and switchboard control. So as I said, we need to make the just dynamic models and also the control module to be controlled for this case. Okay, this is about how to model the generators as an example. So I want to talk, if you use the same equation for generators, and if you use the same parameters to put, then we can have same result from 2 different softwares. So this is a result from Simulink using the libraries called the Syncscape. And this is the result from PSIM. So it's almost the same. I think you couldn't see that, but these result and this result are same. So I want to talk about in this case, you don't need to worry about the result from the softwares. It depends on just the equation and parameters of datasheet, not depend on the software. Back then, I was really in a hurry to make the simulation platform, so I couldn't get many simulation result. In this case, it's a voltage waveform from OSP and from real-time simulator RLP. So we can get this almost the same result except the simulation time, because OSP the performance of OSP is dependent on the local laptop, so it took much time. And this is about results from the testing PMS. So we can see the signal from PMS, such as start generator and connect, disconnect, and increasing speed for load sharing things. So we can see the load sharing was complete, controlled by PMS here. And also my switchboard model worked well. The synchronization logic was working to operate two generators at the same time in parallel here. Actually, there are usually 4 kinds of load sharing: symmetry, asymmetric, fixed, and manual. But I think symmetric load sharing mode is most difficult. So I showed just the symmetric load sharing here. So 2 generators are running at the same time, and I increased the load step by step, and PMS tried to control 2 generators in parallel for load sharing symmetrically here. And this one, we tried to connect and disconnect generators one by one. Then PMS tried to control the generators, like control the generator disconnecting, then reducing load from the generator and adding the more load to another generators like this. And after connecting to two of generators here, then PMS still trying to keep load sharing mode symmetrically. So connect, disconnect one by one, and load sharing and stable step, and increase the load greatly and gradually here. And PMS control 2 generators well, actually. Okay, this is also 2 generators are running at the same time on the same switchboard, and load sharing here, step by step increase load. And here the third generators are running and connecting to the same switchboard. Then 2 generators reducing their load for load sharing. So 3 generators are on the load sharing symmetrically here. And I disconnected the generator 1, maybe, not yellow one. Then still generator PMS tried to control 2 generators for load sharing here. And this is a kind of test procedure. We brought them from FAT procedure and hill testing procedure. FAT means factory acceptance test, and hill testing is hardware in the loop testing here. Yeah, I didn't have enough time for the first project, so I a little bit was in hurry to make it. So I am trying to optimize my power model more. And secondly, I need to prepare for core simulation with engine model, because our second project is about generator engine. So there is some connection between power model and generator engine model. So in KSOE's platform, using each real-time simulator, we already had some core simulation platform using communication protocol, but there were a lot of issues to co-simulate to a real-time simulator, because sometimes communication time can be delayed, then the other simulator has some errors. So we should turn off the simulator model and connect and reset again. And I think the first project model should be modified more changeable, easily replaceable. So I'm working on it already. And actually, we already are checking the communication time between models. So we are using also a real-time communication device. So this means it communicates every 100 milliseconds. So it works, and this is worked as well. But there are more data than this, but still it communicates within 100 milliseconds. So nothing bad happened under this situation. And this one is a kind of HMI to test the PMS. So sometimes it's necessary to control the generators and circuit breakers, and also watching these waveforms at the same time. But when I was using the OSP or Simulation Trust Center, so I should check the waveforms, and I moved to the page of the parameter page, and I came back to the waveform page. So maybe the HMI things can be improved on OSP, or I can make this HMI and just interface through STC. Yeah, I think this is the end. Okay.
Very much. Microphone tried to get away from me. All right, what questions do we have? Thomas? Just let me quickly repeat the question so that people online can also follow along. So the question was with respect to, yeah, because the statement was that OSP was somewhat slow. That's what you found.
Yeah.
And if the other software use Opal, if it does some distribution, and if that, if I understand it correctly, could be part of the issue you experience with the speed.
But when using Simulation Trust Center, there was not any problem about the computation time, but just using OSP, it's a local platform, so following the performance of laptop. So that's why the computation time was slower than the real-time simulator. But when using Simulation Trust Center, it was okay. Yeah, correct. Yeah. You're right.
He tested using a demo application, and what was the second one you said? And the Simulation Trust Center. Okay. We have better solution now for questions. Stian will give you the microphone if you have a question. So then you don't have to suffer through me repeating the questions poorly, probably. Christian.
Thanks for a very inspiring presentation. From strategic point of view, just a comment. I think this is excellent example of how we should motivate our shipyards to use this as a competitive advantage to do this virtual commissioning, which can save you for a lot of money on the sea trial, but it also ensure integration and interfacing in a much earlier phase. That was the comment, and one question was, and that is just because I'm not sure how this is solved. When you are simulating, for instance, electromotor, it is obvious that that must be some just replacement, virtual replacement, some mathematical models. But when you are simulating the PMS, is that exactly this? That is just a software, and that will be a software also on board the vessel. So is that the same as would be on the vessel, or is it separate logics? My question is if you can just implement existing PMS softwares and philosophy. Is that what you have done, or is it like separate things?
Yeah, in this case, we used a real control system, real power management system, interfacing based on multiple TCP/IP protocol, of course, through simulation trust center. So I also tested with my virtual power management system, just the logic. It was just software, and of course it worked as well. So so I can say we already tested with a real control system.
There was we have 2 online questions, so I thought about giving you one of them for now. Can you let me know the detail engine model which was interfaced with the PMS? I guess what was the, you can explain a little bit in more detail the engine model that you interfaced with the PMS.
About detailed engine model?
Yeah.
Okay. Yeah, we have some experience interfacing with our engine model because we have 3 research departments in charge of engine model and power plant model and also a gas system model. So Kevin should know we have the researchers for engine model. It's just in this case, it's about just the power plant model. So I made my own just governor local controller. So it's not that detailed engine model. So it's basically consists of some PI controller and some equations, formulas. So yeah.
I might be wrong about this, but I think in the further work you did say that and the engine model might be a
yes,
natural.
Yeah, one of my department researchers, she already launched modeling the generator engine modeling this year. I think that she's going to get a workshop, the RAMOC, this year. So after that, maybe next year, we try to get the core simulation with the engine model and power model.
And that would be a more involved engine model as well then.
Yeah.
Any more questions or comments from the audience here? Plus? Just wait for the microphone, plus.
Can you hear me? Okay. Just regarding your question, also Christian, this say ever repeating hierarchy in between models that substitute something component wise, right? Like a motor, and then a software like a power management system or any other control system that has possibly an HMI, right? So, and that is in fact a challenge, and I think one that we will face and see repeatedly going forward, because they if we go into virtual testing, there is, conceptual wise, there is not really a fixed separation in between components and systems, because everything that is considered a system is in the next level of the value chain just considered a component. So, and this duality, this just prevails. So whenever we have control systems in between, where say one component manufacturer comes with this control system, and we discussed this also, for instance, for an engine, right? You have an engine, and that engine comes with an engine control system, which is quite sophisticated for an internal combustion engine. So where to say where to separate that from the rest that you would simulate? Where are your system boundaries? How would you set them? Would you say build the engine control system into the engine model, because everything that communicates with that engine model is not really interested possibly into the internals in between the engine control system and the engine? So that is I think an ongoing, an existing challenge that we have. I think probably not everything will be solvable with FMUs. We will not be able to put everything into FMUs. Things that have an HMI might not be able to be put into an FMU. But on the other hand, we need to come up with, say, ways to automatically test also graphs, dependency graphs, systems that are built on each other, where in between somewhere might be a component that is, say, not FMU or not able to be modeled. How to deal with that? We don't know, honestly, right now. I would say, well, that's
stupid question, Klaus. What's HMI?
human machine interface.
That's what I thought. Okay, yeah. Thanks. I'm here also to ask stupid questions, so that was the first of probably many more to come. There was a second online question. Guess we can take a few minutes to go through that too. And that question is, can you comment on how the simulation performance compare between the models ran on Opel RT and on OSP? So a little bit more about the difference in simulation performance between those two.
Okay, I can tell here. It shows about a real-time concept here. So in my area, real-time means calculate all digital models within the fixed time step. So here, so if I distribute my digital model to each cores of Opel RT, then we call that overrun. Overrun means the cores cannot finish the calculation within this fixed time. Then overrun happened. Then I have to optimize my model or distribute my digital model using more cores of Opel RT. But using simulation trust center, it was really good and nice, but I cannot say that it is real time, because it calculates really fast, but I consider that as just a variable time step. So sometimes simulation trust center can calculate so fast here, maybe within just 20 microseconds or 30 microseconds. But sometimes the real-time factor became 2 very shortly. So in that terms of the real time, comparing with the capability of Opel RT, so I can say using Opel RT is more sure solution in this case. But it's about, for example, I mentioned about synchronize the 2 generators. When we tried to co-simulate engine model and power model using each real-time simulator, just using communication protocol, then you know, the sensitivity for each system are different from each other. So at the same time, PMS trying to control the engine model to increase or decrease the speed for load sharing. But at the same time, my switchboard model also trying to synchronize the sine wave in terms of frequency and in phase and in magnitude. So it didn't work actually. So that's why we use this real-time communication device as well, because it ensures the communication time within 100 milliseconds. So the time delay never happens. So we can be sure about data exchange. So I also wondering, when we are trying to co-simulate power and engine interfacing with each control system, like engine control system and power management system, then I think that there could be some issues for exchanging data, because as far as I know, simulation trust sensor cannot ensure this real time in terms of fixed time step. So I think that's the difference between using operator and using OSP.
All right. Thank you very much.